Gibbs looked at the delta S universe equation and thought, well, that's nice, but as a chemist, we use delta H all the time. So instead of using delta S of the surroundings, he put in negative delta H system over T. And the advantage there is that delta H of the system, that's the delta H of products minus delta H of reactants. And chemists have always been really good about that. But obviously, this equation right now is kind of ugly. All right, negative delta H over T plus delta S, pretty funky. So he multiplied everything through by negative T. And when he did that, he got negative T times delta S of the universe equals delta H of the system by itself minus T delta S. And that looked a little bit better. But what people realized is that negative T times delta S of the universe, you can actually think about it as its own thermodynamic quality. And so what people did eventually is negative T delta S of the universe equals another thermodynamic quality called delta G of the system. And delta G is what they refer to as Gibbs Free Energy. And Gibbs Free Energy is yet another thermodynamic quality. So there's delta H enthalpy, there's delta S entropy, now there's delta G Gibbs Free Energy. So if you have standard conditions, delta G equals delta H minus T delta S. This is the Gibbs free energy equation. There's a picture of good old Gibbs up there. Now, at this point, you're probably like, yeah, that's a lot easier. What are you talking about? Well, okay, here's the chemist's perspective. It's easy to calculate the delta H of a reaction, delta H products minus delta H reactants. It's also easy to find the delta S of a reaction. We saw that already, delta S products minus delta S reactants. You've got a table, you'll have delta H and delta S values. Well, if you know the temperature, then you can quickly calculate the delta G value. And delta G is related to negative T delta S. So if delta S of the universe is positive because of the negative T, that means delta G is going to be negative. And if delta S of the universe is negative, negative T times negative means delta G is going to be positive. So you can relate delta G back to the spontaneity. And in chemistry, that's what people do. They're always talking about delta G values and how it relates to spontaneity. But in your own mind, just realize that delta G really comes from negative T times delta S of the universe. And this is all related to second law and stuff like that. Oh, joy. Delta G equals delta H minus T delta S is arguably the most important equation of all of chemistry because we're going to use this delta G to see if a reaction occurs or not, if it's spontaneous or not, all right? And the Gibbs free energy is just literally the energy change for the system minus the energy lost in disordering the system. So delta H now, that is the energy change for the system, and the delta S is the energy lost in disordering the system. Remember, delta S is just a measure of messiness. If you have an exothermic reaction with a negative delta H, and you have an increase in the entropy, which is a positive delta S, look what happens. You have a negative delta H minus a positive delta S. Delta H is negative, delta T minus T delta S is negative. You're always going to have a negative delta G. So if you want a reaction to be spontaneous all the time and product favored, you want a negative delta G. And you will always get a negative delta G, a spontaneous reaction, if you have an exothermic reaction and an increase in the entropy, a negative delta H and a positive delta S. Those conditions with negative exothermic enthalpies and positive increases of entropy will always be spontaneous, always product favored. But we don't always have that because sometimes you'll have, for example, an endothermic enthalpy, which would be a positive delta H, and you'll also have a decrease in the entropy, and that can be a negative delta S. We've seen a couple of those. Well, if delta H is positive, delta S is negative, but negative times negative makes it positive. In those cases, delta G will always be a positive number. So if you end up with a reaction that's endothermic and a decreasing entropy, you will always be in a non-spontaneous state. Those reactions just won't occur. They're going to be reactant favored, or they won't occur to a very appreciable extent like we've seen with equilibrium and stuff like that. So if you want your reaction to go, you want it to be exothermic with a positive delta S. On the other hand, if you do want a reaction not to occur, and there are cases of that, you want a positive delta H and a negative delta S, because those conditions will always give you a positive delta G. So delta G, when it's negative, spontaneity will happen, product favored. But if delta G is positive, you'll have a non-spontaneous reactant favored condition, and those won't be likely to occur. Let's calculate the Gibbs free energy change for this reaction, and there's delta H and there's delta S. So to do this, delta G, which is what we're after, equals delta H minus T delta S. Couple of things. Make sure your temperatures are in Kelvin, all right? Very important in thermodynamics. And second of all, notice that the units there, delta H is often kilojoules and delta S is often joules. So make sure you convert one to the other. Because our answers here are all in kilojoules, I would recommend turning your delta S into kilojoules first before multiplying by the Kelvin temperature. But anyway, plug and chug, delta G equals delta H, and you can see I just used the value as is, minus T, so 25 Celsius is 298 Kelvin, and then the delta S value, which is negative, I turned it into kilojoules. So I divided by 1,000. It became minus 0.10836. Anyway, the number came out to be a negative 568.9. Negative delta G's are spontaneous. So this reaction is going to occur at room temperature, which is pretty cool. The negative sign of delta G tells you the reaction's good to go. If this would have been a positive delta G, we would have said it was non-spontaneous. Non-spontaneous reactions don't occur by themselves. There are 4 conditions of delta H and delta S that are possible, and scientists like to think about this because it affects the sign of delta G. So we talked about earlier how if you have an exothermic reaction and an increase in the entropy, the delta G is always negative. Those are always going to be product favored, spontaneous. Those are going to be good to go. On the other hand, if you have an endothermic delta H and a decrease in the entropy, a negative delta S, then your delta G in those cases will always be positive. And positive delta Gs are the reactant favored non-spontaneous reactions, and those are hard to do. There's 2 more possibilities though. The first possibility down here is when you have an exothermic reaction but a decrease in the entropy. Now in this set, the delta H exothermic, it wants the reaction to go. A negative delta H contributes to a negative delta G. On the other hand, delta S is negative. Delta S says, I don't want this reaction to go. I'm not happy with it. So here, enthalpy and entropy are fighting, all right? Enthalpy wants the reaction to go. Entropy doesn't want the reaction to go. In these cases, then, it really depends on your temperature. Temperature times delta S can overpower delta H. If your temperatures are high enough, then temperature times that negative delta S makes for a positive number. Positive numbers don't contribute to negative delta Gs. So in this case, you would say that high temperatures make the reaction non-spontaneous and low temperatures make this reaction spontaneous. On the other hand, the last set there, it's the opposite. Now we have an endothermic delta H. Endothermic reactions don't really wish the reaction to be spontaneous, but you do have an increase in the entropy. So entropy wants the reaction to go. If entropy times temperature is able to overpower enthalpy, then the reaction will occur. So we say sometimes that in the last case there, that high temperatures make the reaction spontaneous. On the other hand, the condition right above it, we would say that lower temperatures make the reaction spontaneous, because in lower temperatures, enthalpy is able to overcome the entropy values. So these are the ways that chemists think about if a reaction is going to occur or not. And it all comes down, in this context, to delta H and delta S. But if the two of them are fighting, then you have to think about the temperature in order to see if the reaction is spontaneous or not. And remember, spontaneous means negative delta G. Those are the reactions which will occur. Non-spontaneous means positive delta G. Those are the reactions which are not likely to occur. A given reaction has a negative enthalpy and a negative entropy. What can be said about this reaction? Okay, so if it has a negative enthalpy, that's exothermic. And a negative enthalpy does contribute to making delta G negative. But if the entropy is negative, negative times that negative right there makes for a positive term. So entropy here does not want this reaction to go. So this reaction is not product favored at all temperatures because enthalpy and entropy have the same sign. If they have the same sign, then that means they're fighting, all right? And these have the same sign. They're not, one of them is not happy with this reaction. So it's not product favored at all temperatures. It's not product favored at any temperatures either. If you have them being opposite signs, that would be the case of A or D. So if they're both fighting, all right, you have to think about which one wants the reaction to be spontaneous, i.e. which one wants delta G to be negative. And delta H here wants the reaction to be negative. It's a negative delta H. So what we would say here is that if the temperature is lower, all right, then the lower temperature times delta S, which gives you, by the way, a positive number, it won't be larger than the negative delta H. Low and high here are very relative. It depends on the magnitudes of delta H and delta S. But at lower temperatures, delta H should be able to overpower delta S, making the reaction product favored and spontaneous. On the other hand, at higher temperatures, then negative T times negative delta S makes for a positive value. Positive values can overpower delta H if they get large enough, and you'd have a non-product favored reaction. To figure out delta G, all right, the way that people usually do it is delta G equals delta H minus T delta S, all right, and that's a great thing. They call that the Gibbs equation, by the way. But there are other ways to calculate delta G. One of them is if you have a table of Gibbs free energy values, and in that same table of thermodynamic values at the end of problem set number 5, there's a third column. One of the columns was for enthalpy, so enthalpy of products minus enthalpy of reactants. One of the columns was for entropy, entropy of products minus entropy of reactants. Well, the third column, guess what? Gibbs free energy values. Woohoo! And Gibbs free energy, if you have all of them, will equal Gibbs free energy of the products minus Gibbs free energy of the reactants. And probably if you have the values, this is the easier way to go. You can always do delta H minus T delta S, but you'd have to do delta H separately, delta S separately, and then in the third step, combine them. If you have all the delta G's, then man, delta G products minus delta G reactants, the way to go. Here are values of Gibbs free energy. And again, every table will be a little bit different. Gibbs free energy values are more like enthalpy values. They can be positive, they can be negative, and also they're equal to 0 for elements in their standard states. So this is very similar to the delta H values. If you look through those, the elements are always 0. Delta H values can be positive or negative. All of these are just numbers, though. You don't have to know any of them. You'll always be given the values on quizzes and exams and stuff like that. And again, like the other examples we've seen, if you take all the Gibbs free energies of the products and subtract all the Gibbs free energies of the reactants, you are good to go. Here's a reaction. We can calculate the delta G, the Gibbs free energy change for this reaction, diamond plus oxygen going to CO2. But notice here that I only gave you two values. I gave you diamond and CO2 only. Okay, for Gibbs free energy values, as well as enthalpy, end elements in their standard states will have values of 0. So in this reaction, oxygen is an element in its standard state. It's going to have a delta G value equal to 0. It would also have a delta H value equal to 0. Elements in their standard states are 0 for both delta H and delta G. They are not 0, though, for delta S, or the S values. Entropy values are always positive, except for those perfect crystals at 0 Kelvin, which is like never. So always look up entropy, but the Gibbs free energy and delta H values here will be 0. So anyway, what you need to do is take the CO2 value and subtract the diamond from it. If you do that, you end up with negative 397.3 kilojoules per mole. Notice that diamond is not the natural state of carbon. The natural elemental state is usually graphite. So that's why you have a non-zero value there for delta G. Let's figure out the delta G of some other reactions. Let's combust carbon into carbon dioxide, so graphite plus oxygen making CO2. Products minus reactants, graphite and oxygen are both 0, like we talked about, negative 394.4 kilojoules. This says that forming CO2 is spontaneous. It's a negative delta G value. Carbon dioxide should form easily, and it absolutely does. Unfortunately for us, it forms too easy. This is the greenhouse gases kind of thing, causing global warming and all that kind of temperature changes and stuff. It forms actually very easy. Carbon dioxide does. So in this case, yes, it forms readily, negative delta G, for better or worse, as you can see. But anyway, that's neither here nor there. We can at least predict now if a reaction is going to occur or not. CO2 should absolutely form. Chemists talk about reactions as being enthalpy-driven and entropy-driven. An enthalpy-driven reaction is just a reaction where the enthalpy contributes to spontaneity. Now remember, spontaneity means negative delta G. And if you want a negative delta G, then you're going to ideally have a negative delta H. So an enthalpy-driven reaction is just a reaction that's exothermic. It has a negative delta H. An entropy-driven reaction means that your delta S value is positive. Positive delta S's contribute to negative delta G's as well. Some reactions are both enthalpy-driven and entropy-driven. Some reactions are enthalpy or entropy-driven, and some reactions aren't driven by either one. Just depends on the conditions. But looking at the sign of delta H and the sign of delta S, you can tell what's up.
When we pour sodium carbonate into hydrochloric acid, it dissolves rapidly to produce aqueous sodium chloride and gaseous carbon dioxide. In this case, entropy increases, and the reaction is energetically favored to occur. It is both enthalpy and entropy driven.
In this video, first of all, you saw something happen, all right? And just seeing something happen means that that reaction is spontaneous. So we would say the sign of that reaction, negative delta G, okay? In addition, lots of energy being given off. Things were bubbling. You would feel warm, I'm sure, if you felt the thing. That means it's an enthalpy-driven reaction, all right? Delta H is going to be negative. And finally, you saw all the bubbles form. Remember that entropy loves making gases. Gases have higher entropy than the things they come from. So this reaction is definitely entropy-driven. We saw the bubbles. Enthalpy-driven. Lots of energy release. That's what enthalpy is all about, exothermic. And finally, it's spontaneous because we saw something happen, all right? So this reaction has all the good things going for it. It's going to happen. Doesn't matter what conditions. This reaction's good to go. But not all reactions have favorable enthalpy and entropy values. We're going to look at that now here in a little bit. Let's look at the combustion of acetylene. Acetylene, which is used in torches a lot of times for welding and stuff like that. Acetylene is C2H2. It reacts with oxygen to make CO2 and water in a combustion reaction. I'm doing it here per mole of acetylene, so that's why the fraction is there. Fascist fractions. But anyway, we can use the enthalpies of formation to calculate the enthalpy of this reaction. So to get that negative 1238 number, and I encourage you to do it, you would take the enthalpy of the products and subtract the enthalpy of the reactants. So for this reaction, you take 2 times CO2 plus water, and all is gases, by the way, minus the enthalpy of C2H2, but you don't really need to calculate or find out the delta H of O2. Elements in their standard states are zero, so you don't have to worry about that. Anyway, if you do that, you should get a number, negative 1238 kilojoules per mole. This is a negative delta H, so that means this will be an enthalpy-driven reaction. You can do the same kind of process, but to find the entropy change, okay? Now, an entropy change, a delta S, would also be delta S of products minus delta S of reactants. And you have to look up everything on there. It would be 2 CO2s and a water minus the entropy of C2H2 and 5 halves O2. You do have to look up the entropy of O2 on this one because all elements and compounds have positive entropies as long as you're not at 0 Kelvin in that pure crystal. So if you do that, you should get negative 97.4 joules per Kelvin. Now, first of all, let's look at the sign. This is not an entropy-driven reaction. This reaction is not favored by entropy. And if you look at that reaction, you're going from 5 halves is 2.5 plus 1. You're going from 3.5 moles of gas to 3 moles of gas. So you're going from more disorder, more moles of gas, to less disorder, less moles of gas. Entropy's not happy with that. So entropy here is a negative number. Now, because delta H was in kilojoules, sometimes it's useful to turn your delta S into kilojoules as well, and that's what I did. You could also turn delta H into joules if you'd rather, doesn't matter. Anyway, delta G of the overall reaction, delta H minus T delta S, and let's assume that someone's welding at room temperature. There's the delta H, there's the delta S value. Delta G comes out to be negative 1209 kilojoules per mole. Negative delta G means the reaction's going to occur. It's spontaneous, it's product favored, all right? However, entropy is not happy with this reaction. Entropy doesn't want this reaction to occur. This reaction only occurs because enthalpy says, hey, I want this reaction to go. This reaction is enthalpy driven. So this is an example where enthalpy and entropy are fighting each other. Enthalpy is overpowering entropy at this temperature. The reaction comes out to be negative, spontaneous. Hey, go for it. Weld your stuff away. And that's good because everybody that welds wants to do welding, I would assume. They couldn't do that if that delta G value would have been a positive number. The dissolution of ammonium nitrate may not be the most exciting reaction to watch, but as we've seen earlier, adding ammonium nitrate as a solid to water, it does dissolve, okay? Because it dissolves, that means this reaction is spontaneous. Remember, if something happens, that means the reaction is spontaneous, but this reaction is endothermic. It takes energy out of the system, the temperature goes down. This reaction is not enthalpy driven. If you have an endothermic reaction, the reaction is not enthalpy driven. But because the reaction is spontaneous, i.e. it happens, you have to have the reaction be either enthalpy or entropy driven. It certainly is not enthalpy driven. This reaction must be entropy driven. Something has to be the driving force to make the reaction occur, all right? And it certainly isn't enthalpy here. So this must be an entropy-driven reaction. And let's check this out.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So we're seeing here again that this is endothermic, so this is not enthalpy driven, but the reaction occurs. You're seeing the solid dissolve. So it is spontaneous. A spontaneous reaction must be enthalpy or entropy driven. Entropy must be helping this reaction to occur. Let's calculate the actual dissolution of ammonium nitrate into a solution of ammonium nitrate. And if you look up these values in thermodynamic tables, all right, you'll find that the delta H, sure enough, is positive. And that's what we expected, all right? It's a positive endothermic number. We saw the temperature of the solution decrease. On the other hand, the entropy of this reaction, positive, all right? Going from a very well-organized solid to a solution is usually a entropy-favored reaction. So the entropy here, positive 108.7 joules per Kelvin, or in kilojoules, positive 0.1087 kilojoules per Kelvin. So if you combine these two into the delta G reaction, sure enough, delta G, negative 6.7 kilojoules. Remember, negative delta Gs are the spontaneous reactions. Those are the ones that something happens. And sure enough, this stuff does dissolve, all right? Again, not as exciting as the other reactions necessarily, but if you see something happens, then delta G must be negative. And it wasn't happening because of enthalpy, that's for sure. Enthalpy doesn't want this reaction to go. This reaction is occurring because of entropy. This is an entropy-favored reaction. This is product favored. It's got a negative delta G. Remember, negative delta G means product favored, it means spontaneous, etc., etc. This reaction is entropy driven. Positive delta S's mean the reaction's entropy driven. Negative delta H's mean that it's enthalpy driven. This is not a negative delta H, this is positive delta H. Enthalpy doesn't want this reaction to go. It only happens because of entropy.